This is Unit 8, Video 11, where we are continuing our discussion of acids and bases. So let's review the idea of a strong versus a weak acid. This is a very important distinction. So strong acids, they will dissociate completely when you put them in water. Remember that acids are defined in their relationship to water for the time being. And just like ionic compounds that dissolve, strong acids will dissociate completely. And to write an equation for it, we use a single arrow. So here hydrochloric acid is shown as dissociating completely into H plus and Cl minus. Now this means that if you have 4 moles of HCl, you will end up with 4 moles of H plus and 4 moles of Cl minus in solution. In fact, all of this will be gone in solution, and the solution will simply contain these two, solvated by water, surrounded by water molecules. Whereas a weak acid will dissociate only partially. And we use a double arrow for this. This is actually an equilibrium arrow, which we will introduce some more in this chapter. We'll talk about equilibrium. And if you have 4 moles of this acid, this is famous for being acetic acid. This is the vinegar-based acid. If you have 4 moles of this acid, in solution you may just have 0.3 moles, we'll say, of each of these. 0.3 moles. Now, so where did the other 3.7 moles go? Well, they actually remained in this acidic form. So you have 3.7 moles on this side. And that's the idea. So this does not dissociate completely. So in water, most of the substance will remain as acetic acid, as the undissociated form of acetic acid. And this is a pictorial representation of the same thing. Now it's important to understand that acetic acid is very soluble in water. It's actually extremely soluble because it has hydrogen bonding in it. If you analyze this molecule, you see actually it has OH group as a hydrogen bonding group. So very, very soluble in water. But it dissociates only 1%. So only a very small percentage of the acetic acid dissociates. Whereas something like hydrochloric acid will dissociate 100%, and it's also soluble. Actually, hydrochloric acid is less soluble than acetic acid. Hydrochloric acid does not have hydrogen bonding in itself, whereas acetic acid does. So both solubility and being a weak or strong are different things, two different things. And again, here we have a strong acid. The main point here is all the molecules will dissociate, will break apart. You won't have any stuck together if it's a strong acid. Whereas if you have a weak acid, you will find in solution a bunch of molecules that are stuck together, that are undissociated. And this is different for different acids. So for example, the weak acid, phosphoric acid, will dissociate to a different extent than acetic acid. Every weak acid has an extent to which it dissociates, and we will actually dive into this a little deeper in a later video. So we have 7 acids that are considered strong acids. 3 of them are binary: hydrochloric, hydrobromic, hydroiodic. Notice that hydrosulfuric is missing, so HF is not a strong acid. In fact, it's a famous weak acid, even though it has dangers of its own, but it does not dissociate. That's what we mean. It does not dissociate. So these are your binary acids. And then we have 4 oxyacids that are strong acids. So we have nitric, sulfuric, and perchloric and chloric. Chloric and perchloric here. And the one that's lower, the chlorous and hypochlorous, are actually weak acids. So it's interesting that in the universe there are only 7 strong acids, and I like the number 7. So make sure to memorize these as the 7 strong acids. It's a good idea to know them. Everything else is then a weak acids. There are thousands upon thousands of weak acids. A lot of them are actually based on organic acids, which come from plants or animals and so forth. The famous weak acids here that we've discussed were phosphoric, carbonic, and acetic, the vinegar-based acid. But there are plenty more. So here is boric acid. Here is chromic acid. This is chromate. The polyatomic ion chromate makes chromic acid. And you have methanoic, you have propanoic, butanoic. These are all organic acids. So plenty of acids in organic chemistry, carbon-based chemistry. All right, let's talk about bases. Now bases, we said at the beginning of the last video, produce OH hydroxide ions in water. And to the taste, if you do a little taste test, they will taste bitter. And they're also electrolytes because they produce ions. Anytime you produce an ion, you will be an electrolyte. To the touch, they actually feel slippery, which is opposed to acids. You can't really feel any difference between an acid and water, but bases actually feel slippery. you can know that you have a base on your hands if you feel like the chemical is slippery. And soap is famously a base. So soaps are actually bases. In fact, to make soap, you use one of the most famous bases in the world. It has the street name of lye, and lye is actually sodium hydroxide. The most famous of the bases is sodium hydroxide. By itself, this is a pretty potent compound. It can actually dissolve glass if it's dissolve glass away in its pure form, and it's actually used to make soap. Once the soap is made, this is converted, so it's just a reactant that's used to make soap, and it's no longer that strong. Generally, there is no reaction with metals. There could be exceptions. A famous exception is actually aluminum. Aluminum will actually react with sodium hydroxide to form the same thing acids form hydrogen gas. Carbonates are considered bases. So in fact, we talked about how acids react with carbonates. Well, that will be an acid and base reaction, which we'll consider in a little bit. In terms of the reaction of hydroxide, so the formula usually ends with OH if it's a base, not always, but usually, and it turns litmus paper blue. So the indicator that turned red in an acid now turns blue in a base, and it turns the other phenolphthalein indicator we've talked about pink. A phenolphthalein indicator is actually used a lot for laboratory determinations of an acid or a base solution, and we'll do a number of these experiments hopefully, and you go from clear to pink if you're in a base. So these are used in household cleaning supplies. For example, baking soda is the most famous cleaning substance. Baking soda is actually a base. Drano is a very strong base. This actually usually contains the active ingredient sodium hydroxide, which clears, declogs, essentially dissolves away anything that's causing a blockage in the drain. So it has to be a powerful substance, and usually they use sodium hydroxide. And ammonia is another famous cleaner. Ammonia is actually a weak base. Ammonia is one of those bases. Remember, ammonia is NH3, one of those bases that actually does not end with OH. So there are some exceptions. So ammonia would be one that does not end with OH, but it still produces OH minus solution. By the definition, it still works. It just produces it in an indirect way. And these are found in antacids, which help remove heartburn, they call it. The heartburn is actually just acid that moves up the esophagus and irritates, stomach acid that irritates the esophagus. So you can actually neutralize that with carbonates, which acids react with carbonates. But bases are carbonates, and that's the idea. Here's some examples of strong and weak bases. So the strong bases usually end with an OH. So sodium hydroxide, definitely the most famous laboratory base. Potassium hydroxide is usually the second most famous. It can be used in some applications that sodium can't be used in, but the two do the same thing. Magnesium hydroxide is a strong base. So anything that's a soluble hydroxide, if it dissolves in water and it's a hydroxide, it'll be a strong base. Famous weak bases then is ammonia. The most famous weak base of all is ammonia. This is baking soda. Sodium hydrogen carbonate, sometimes called sodium bicarbonate. That's baking soda. And many other organic bases contain nitrogen. They're called nitrogen-based organic bases. In fact, the base in DNA, if you remember, the DNA has bases. It literally has a nitrogen-bearing base, chemical base. So the bases are actually, in DNA, the bases are called the basic substance, but each of the bases actually is basic because it contains nitrogen in it. Okay, let's talk about some reactions between acids and bases. So it turns out that an acid and a base will react to produce salt and water. And what will happen is, why don't we finish this up in the next video? So we'll actually dive much deeper into this and be able to write some reactions for ourselves in the next video. So we'll wrap up video 11 here.